Okay, so how did a renegade, brilliantly unorthodox English theologian, a farm boy from Illinois, and a 25-year-old chemical engineer manage to literally build the foundations of our modern world? I know, it sounds exactly like the setup to a strange joke, but I promise you it's the 100% true story of how human curiosity fundamentally transformed the reality we all live in today.
Welcome to This Explainer. Today, we're taking a really fascinating journey through the history of science, guided by the incredible archives of the American Chemical Society. For 150 years, the ACS has been out there empowering scientists and championing trust in chemistry. And through their National Historic Chemical Landmarks program, they've basically been documenting the exact moments where a lab breakthrough completely reshaped society.
Okay, let's dive into this. And we really need to consider the sheer scale of the stuff we're talking about today. These aren't just, abstract, dusty academic concepts. We are talking about bacalate, the world's first totally synthetic plastic. We're talking about the commercialization of nylon, the mass production of penicillin during World War II, the invention of Scotch tape, and yeah, even Tide laundry detergent. Every single one of these is an ACS National Historic Chemical Landmark. They're everyday items that all started as revolutionary chemical milestones. So, to grasp how this whole field evolved, here is our roadmap for today. First, landmarks of chemical history. Second, Priestley and the oxygen discovery. Third, NIST, standardizing the modern world. Fourth, the radiation chemistry revolution. And finally, shaping the future of chemistry.
Starting off with Section 1, Landmarks of Chemical History, exploring the ACS legacy.
Let's jump right into Section 2, Priestley and the oxygen discovery, unlocking the air. All right, to really get Priestley's impact, you first have to understand the scientific stakes back then. Specifically, a little thing called phlogiston. For 23 centuries, literally stretching all the way back to the ancient Greeks, scientists firmly believed that air was just a simple, unalterable element. And in the 18th century, the dominant theory of fire was that flammable materials contained this mysterious substance called phlogiston. When something burned, it supposedly released this phlogiston into the air until the air got completely saturated and then the flame just went out. It's a charmingly primitive misconception to us now, but back then, that was accepted as absolute scientific fact. Enter Joseph Priestley. And wow, his life was anything but boring. He was a dissenting minister who just casually taught himself multiple languages and perspective drawing. In 1767, while living next to a brewery, he started investigating the gases from fermentation and actually invented carbonated water. So yeah, he pretty much laid the groundwork for the modern soft drink industry. Then, in 1774, he makes his massive discovery of oxygen. But his vocal support for both the American and French revolutions, along with his highly unorthodox religious views, really enraged a lot of people in England. In 1791, an angry mob actually burned down his home and laboratory, and by 1794, he was forced to flee, emigrating to Pennsylvania, where he kept up his research. The real breakthrough moment happened on August 1, 1774. Priestley used a 12-inch glass burning lens to focus sunlight on a lump of reddish mercuric oxide inside an inverted glass container. It emitted a gas that he famously noted was, quote, 5 or 6 times as good as common air. A flame burned incredibly intensely in it, and mice lived much longer in it. Now, because he was still operating under the old theories, he called it dephlogisticated air. But when he shared this with the French chemist Antoine Lavoisier, Lavoisier realized what it truly was, named it oxygen, and used it to completely overthrow the phlogiston theory, sparking the chemical revolution.
Moving on to Section 3, NIST, standardizing the modern world, measuring the century.
To see how this all connects to our modern infrastructure, we've got to meet Samuel Stratton. He was a farm boy from Illinois who actually paid for his first year of college by selling a colt he raised. He became a brilliant physicist and the very first director of the National Bureau of Standards, which we now know as NIST. And the contrast of that era is just wild. Before NIST, American industry was completely fragmented and chaotic. A foot in Illinois was literally a different length than a foot in Virginia. There were 8 different values for a single gallon. Timekeeping was strictly local. It was a total nightmare for both commerce and science. But after NIST was established under Stratton, they rapidly brought scientific order, establishing universal, rock-solid standards for length, mass, temperature, light, and time. And in chemistry, standardizing materials was absolutely crucial. Under NIST's incredibly exacting chief chemist William F. Hillebrand, a guy so rigorous, his staff actually called him the Supreme Court of Analytical Chemistry. The Bureau created a massive catalog of standard reference samples. By 1925, they had cranked out a staggering 5,000 standard reference samples, representing 65 different materials. Think about it. If the railroad industry needed to stop their cast iron wheels from randomly fracturing, NIST was the place that provided the exact chemical standard for the iron.
But NIST didn't just measure things. They catalyzed some unbelievable technological advancements. They designed luminous script signs back in 1904, which was the very first use of neon for displays. They pioneered the methods for broadcasting time on TV in 1971, which, amazingly, gave us closed captioning. In 1974, they helped develop the first standards for smoke detectors. And in 1992, they released the first standard for DNA profiling, completely paving the way for it to be accepted as real evidence in court. Just absolutely vital, everyday work.
All right, Section 4, the Radiation Chemistry Revolution, Designing High-Tech Materials.
So after World War II, the government is scrambling to find peacetime commercial uses for atomic energy. Enter Paul Cook, a 25-year-old chemical engineer who looked at high-energy radiation and literally saw the future of manufacturing. So the crucial point here is understanding how this radiation actually changes materials at the molecular level. It basically happens in 3 steps. Think of polymer molecules like incredibly long, thin chains of beads. First, an electron beam strikes the material and knocks away hydrogen atoms. Second, this leaves behind highly reactive spots, called free radicals, right there on the chains. Third, these free radicals on neighboring chains migrate together and bond. They essentially lock the individual strings of beads together into this incredibly tough 3D network.
Now, what's really interesting about this process is the actual superpower it unlocks: elastic memory. Cook founded a company called Raychem, and he rented the very first industrial high-energy electron accelerator to cross-link these polymers continuously. Because the molecules are locked together, if you heat the plastic, stretch it out, and let it cool, it actually holds that new stretch shape. But, and here's the crazy part, the moment you heat it again, it remembers its original shape and violently shrinks right back down to it. Raychem used this mind-bending elastic memory to create heat-shrinkable tubing that tightly sealed electrical wires for aircraft and extreme military environments. They basically invented a multi-billion-dollar industry completely out of thin air.
Which brings us to our final section, Section 5. Shaping the Future of Chemistry, a Legacy of Innovation.
So, when we take a step back and look at the whole 150-year arc of these ACS landmarks, we aren't just looking at a list of isolated inventions. We're really looking at the evolution of the scientific method itself and how we continually harness it to solve human problems. And this brilliantly illustrates that exact evolution. With Priestley in 1774, chemistry was a philosophical curiosity, a guy in a room with a magnifying glass trying to understand the invisible air, which inadvertently gave us the soft drink industry and our whole modern understanding of combustion. Then, with Stratton in 1901, chemistry becomes this essential governmental infrastructure, creating the unified standards we desperately needed for safety and mass production. And finally, with Cook in 1957, chemistry becomes a highly advanced commercial application, safely harnessing atomic-age tools to engineer advanced polymers for the most extreme environments on Earth. From standardizing a simple gallon of milk to literally manipulating the atomic structure of plastics, these landmarks prove that chemistry is the ultimate tool for improving the human condition. Today, there are thousands of scientists standing right on the shoulders of Priestley, Stratton, and Cook. They're using these established fundamentals to tackle massive issues like climate change, to engineer new medicines, and to design truly sustainable materials. Which leaves us with one incredibly exciting question to ponder. As today's chemists work tirelessly in labs across the globe to solve tomorrow's problems, what is going to be the next historic chemical landmark? Thank you so much for hanging out with me on this explainer. Keep asking questions and keep exploring the science that shapes our world.